class, welcome back to thermodynamics. In this lecture, we are going to be looking at vapor compression refrigeration systems. So remember, the goal of a refrigeration cycle is to move heat against its heat flow against its natural gradient. So meaning that we're forcing heat to flow from the lower temperature reservoir to the higher temperature reservoir. So we're going to go through 3 examples today, 2 problems dealing with the refrigeration cycle, and the third looking at heat pumps. So this is number 10.10 from your book. Refrigerant 22 enters the compressor of an ideal vapor compression refrigeration system as saturated vapor at minus 40 degrees Celsius. So with the refrigeration cycle here, what we're doing is we're starting going into the compressor, whereas analogously looking at a power cycle or a power plant, we were starting pushing vapor through a turbine. And so here we're starting at state 1, going into the compressor. Our initial temperature is minus 40 degrees Celsius, which, in case you're curious, is conveniently the same as minus 40 degrees Fahrenheit. We're dealing with saturated vapor. So remember, this tells us that our quality is 1 there. And we have a volumetric flow rate of 15 meters cubed per minute. I like to call this V.1. I think that's a little clearer. And so V.1 is 15 meters cubed per minute, which is equivalent to 0.25 meters cubed per second. And the refrigerant leaves the condenser at 19 degrees Celsius. So we're going from the compressor through the condenser, and the condenser holds constant pressure at 9 bar. And we get out at T3 is 19 degrees Celsius. And then we go through an expansion valve, which is a throttling device, and we'll talk about that more a little later. So first, it says determine the compressor power in kilowatts. So the power that's going into the compressor, the refrigerating capacity in tons, and the coefficient of performance. So remember, that's beta for our refrigeration cycle, and the rate of entropy production. So looking at a TS diagram, just to get a sense of what's going on. So remember, at state 1, we're starting at minus 40 degrees Celsius, and we're at x1 equals 1. We're going through a compressor, and so here we have, this is an ideal vapor refrigeration cycle. So this would be a Carnot cycle, similar to a Carnot cycle. So for an ideal vapor compression refrigeration cycle, the key here is you're not getting entropy production through the compressor. All right, so we have constant entropy here. And what we're doing is we're riding along an isobar. So P2 is equal to P3 is equal to 9 bar. So there's our isobar. All right, and remember, it's even underneath the vapor dome. Okay, so there's our isobar, and then we're dropping, and then we're at T3, which is 19 degrees Celsius. And then for state 4, we're back at minus 40 degrees Celsius, and we're somewhere in the vapor dome. So what we're going to do here is we're going to go through quickly and look at our properties at each state. So I am going to just start writing it in here, and what I'm going to do this time is I'm not going to run through every single step of looking up in the table, of interpolating. If you want more detailed practice with that, go back to last lecture and review that. But I'd like to get through a lot of stuff today, and so I'm just going to write it down. And so feel free to pause, try it out on your own, and see if you come out with these same properties. So state 1, T1 is minus 40 degrees Celsius, and X1 is 1. And so that tells us, if we look it up in the tables for refrigerant 22, H1 is 233.27 kilojoules per kilogram. And also S1, so remember our quality is 1, is going to be 1.0005 kilojoules per kilogram Kelvin. So then for state 2, so remember this is ideal, and so the key here is, yeah, we know that pressure is 9 bar, but we also know, because this is an ideal vapor compression refrigeration system, that S1 is equal to S2, so we don't have a change in entropy there. And so via interpolation in the tables, this one would be an A9. In the text, you can find that H2 is 287.55 kilojoules per kilogram. For 3, I'm going to put that one over here. We have a compressed liquid because it went through a condenser. And you can see that here, our compressed liquid, are outside the vapor dome. And so we know the temperature is 19 degrees C. So because we're dealing with a compressed liquid, H3 is going to be approximately where we have a quality of 0 in the liquid vapor table. So HF at 19 degrees Celsius, which is going to be 67.87 kilojoules per kilogram. And then the other piece now is from that, let's see, we also know that S3 is going to be 0.2566 kilojoules per kilogram Kelvin, just from the tables. And then for 4, from 3 to 4, we have an expansion valve, and this is a throttling process. And with a throttling process, H3 is equal to H4. So the key with a throttling process is that you have no change in enthalpy over the process. So enthalpy, not entropy. So delta H is 0. And so we can go into the tables, and we know that T4 is minus 40 degrees C. And so we need to go ahead and we're in the vapor dome, under the vapor dome. So we go to our liquid vapor saturation tables. We look for a temperature of minus 40 degrees C. We interpolate for H4 equal to 67.87 kilojoules per kilogram. And we can get our quality. So our quality, if we do that, is going to be 0.7091. And using our quality, we can get our entropy, which is 0.7095 kilojoules per kilogram Kelvin. All right. And so now let's go through and let's figure out the compressor power. Okay, so this is 1010. All right, so for A, the compressor power, so this is going in. So there is one thing we definitely need to know first, and that is the mass flow rate of our refrigerant. We were given our volumetric flow rate, but we need to find our mass flow rate. And so m dot, if you remember, is equal to our volumetric flow rate, which is in meters cubed per time, so volume over time, divided by specific volume, which is volume per mass. And so that means to get the mass flow rate, we need to look up V1 in our tables. And V1 for X1 is 1, the quality is 1 there, is going to be 0.2052 meters cubed per kilogram. And now we can get the mass flow. And so our volumetric flow rate we determined was 0.25 meters cubed per second divided by 0.2052 meters cubed per kilogram. And this is going to give us a mass flow rate of 1.218 kilograms per second. Now for B, didn't finish, I got ahead of myself. We just got our mass flow rate. We did not get our compressor power yet, clearly. Let me get my pen back. So the compressor power is going to be W dot C is equal to, one second. So the compressor power, if we look back, remember the compressor is up 1 to 2. So W dot C is going to equal M dot H1 minus H2, which is going to be 1.218 kilograms per second. And H1 we determined was 233.27. And H2 was 287.55, and this is in kilojoules per kilogram. And so we end up with minus 66.13 kilowatts. So that's power going in. So if you're thinking about, we could say there's 66.13 kilowatts going in, or overall it would be, we're putting power into the system, so we have a negative. All right, so now let's look at part B. And for B, we were looking for the refrigerating capacity in tons. So for refrigerating capacity, we need to look at Q in, and that's going to be M dot H1 minus H4. So this is at the evaporator right here. That's how we get the refrigerating capacity, which is going to give us 201.46 kilowatts. And we were asked to convert it to tons. So there's 0.284 tons per kilowatt. And so we get 57.2 tons is the refrigerating capacity. Now, we're going to do C. So for C, we were looking for the coefficient of performance. So beta is going to be equal to H1 minus H4 over H2 minus H1. So this would be our Q in over WC. And so this is going to give us 3.05 when we plug in our enthalpies. For D, we now have to determine the entropy production. So Q dot out is equal to M dot H3 minus H2. which is going to give us minus 267.64 kilowatts. And so the entropy production for an ideal vapor compression refrigeration cycle is given by Q dot out minus Q dot out over T3 minus Q dot in over T1. Okay, and so just remember T3 is our 19 degrees Celsius and T1 is our minus 40, and we got to convert them to Kelvin in order to use these ratios. And so it's going to be minus 267.64 kilowatts divided by 292 Kelvin minus 201.46 kilowatts divided by 233 Kelvin. And this will give us an entropy production of 0.052 kilowatts per Kelvin. Okay, so that is it with that one. For this next problem, we're going to look at, we're going to continue on with the refrigeration cycle, but we're going to look at one that is not ideal. So there's going to be an extra level of complexity. There's going to be a change in entropy as we move through the compressor. So let's take a look at this. This is number 1024 in your book. Window-mounted air conditioner, and in case you don't know what one looks like, there's an image below, supplies 19 meters cubed per minute of air at 15 degrees Celsius and 1 bar to a room. Air returns from the room to the evaporator of the unit at 22 degrees Celsius. The air conditioner operates at steady state on a vapor compression refrigeration cycle with refrigerant 22 entering the compressor at 4 bar 10 degrees Celsius. Saturated liquid refrigerant at 9 bar leaves the condenser. The compressor has an isentropic efficiency of 70%, and refrigerant exits the compressor at 9 bar. Determine the compressor power in kilowatts, the refrigeration capacity in tons, and the coefficient of performance. So this is very similar in strategy to the Rankine cycle problems we've been solving. So why don't you try this one on your own first and then come back together and we can go through it. So pause it here and then continue. So let's sketch out our cycle. So starting at our compressor. So we have W dot C. We're given an isentropic efficiency of 0.7. We're given a pressure of 2 bar. No, sorry, of 9 bar. Actually, let's not try that yet. Let's just draw this. There we go. Let's add our numbers. So this is 1. And we're dealing with air. And I'm going to do this in a different color so we can see. P1 is 4 bar. And T1 is 10 degrees Celsius. Okay, so then here we're at state 2. And P2 is 9 bar. Then we go through our condenser. And we have Q out here. And then we're going to come out at state 3. go into our throttling device or our valve. And we're going to go into our evaporator. Okay, so what we're looking at here, let's see, what else do we know? We know we have a Q in here. And we have refrigerant 22 enters the compressor at 4 bar and 10 degrees Celsius. So we have see. Let's not deal with that part yet. Let's move on to X3. Quality here is 0. It's going to be saturated liquid. P3 is still 9 bar. And as the working through fluid down here, we have T in at 22 degrees Celsius. So I'll do different colors. It's a different line. We have T out. It's going to be 15 degrees Celsius. One bar. So this is our air down here. So this is the part of the unit that is interacting with the room. And we have V dot out is 19 meters cubed per minute. Okay, so this is, I'm going to make this clear. This is R22 up here. Down here is air. Air. Okay. And I think I've gotten most of it here. So let's draw our TS diagram. We're under the vapor dome. A lot of it. So we're out here for state 1, 2, following an isobar, 3, 4, and back. All right, so there is our TS diagram. So let's get started with our analysis of each state. All right, so starting at state 1. Okay, so H1 is going to be 259.18 kilojoules per kilogram. That's from table A9. So for R22, with a pressure of 4 bar and a temperature of 10 degrees Celsius, and S1 is 0.9795 kilojoules per kilogram Kelvin. Now, because we're dealing with a real cycle here, we're given an isentropic efficiency, so we're going to have to look at both the isentropic state 2 and the real state 2 here. So we have to use the isentropic state 2 to determine the enthalpy at the real second state. So for state 2, S. So for the isentropic state, S2S is equal to S1, which is 0.9795 kilojoules per kilogram Kelvin. And from that, we can find H2S is 280.68 kilojoules per kilogram. So now we can figure out H2. So the isentropic efficiency of the compressor is equal to H2S minus H1 divided by H2 minus H1. So that is going to give us that H2 is equal to H2S minus H1 divided by eta C plus H1. So plugging in our values there, we get that H2 is going to be 289.89 kilojoules per kilogram. Okay, so now let's move on to state 3. So for state 3, we know that, one second. For state 3, we know the pressure is at 9 bar. The quality is 0. And so looking at our tables, we can figure out that T3 is 19.59 degrees Celsius, and that H3 equals 68.59 kilojoules per kilogram. So remember, we're under the vapor dome there. And that S3 is 0.2591 kilojoules per kilogram Kelvin. Now for state 4, once again, we have a throttling device, and P4 is equal to P1, which is 4 bar. Okay, and so knowing that H3 is equal to H4, which is 68.59 kilojoules per kilogram, we can find that T4 is minus 6.56 degrees Celsius. And from there, we can get the quality knowing the enthalpy. So X4 is going to be 0.148. And once again, review last lecture if you want to see this out step by step. And S4, using that quality, we can get S4 is 0.266 kilojoules per kilogram Kelvin. Okay, so now we have our properties set for each state. So now we can go ahead and determine the power input into the compressor, the refrigerating capacity, and the coefficient of performance. So let's take a look. Okay, so first we're going to do part A, and we're looking for W dot C, which is going to be M dot for our R22, refrigerant 22, times H2 minus H1. And so this is going to be equal to, we need to find M dot actually. Let's find M dot. So The way we find m dot is by going ahead and looking at our evaporator, because we have air that we know the mass flow of, we know the input and output temperatures. So let's go analyze that first. So we know that m dot air in the evaporator is going to be v dot air, P, times pressure, divided by R air times T6. So this is just the ideal gas law. So T6 would be our temperature out, which is 15 degrees Celsius. And so we have our mass flow rate. We have 19 meters cubed per minute, our volumetric flow rate. And we have 1 minute is 60 seconds. And our pressure we're given is 1 bar, so that's 100 kilopascals. And we divide by the gas constant for air, 0.287, and 15 degrees Celsius, which is 288.15 Kelvin. Okay, and so we get a mass flow of air, a mass flow rate for air of 0.383 kilograms per second. And so now we have to do our mass balance or our energy balance. So 0 is going to equal m dot for R22 times H4 minus H1 plus m dot air H5 minus H6. And so we need to look up H5 and H6 in the tables for the given temperatures of air for 22 degrees Celsius. So remember to convert it to Kelvin first. And for 15 degrees Celsius. And so we end up with our mass flow, or we could also use the we could also use the CV or the CP in the tables as well for some in between. So m dot is going to equal m dot air, and we can use CP for air because the temperatures are close together. So at maybe like 20 degrees C would work, of T5 minus T6 divided by H1 minus H4. And so we end up ultimately with a CP air of 1.005, and our delta T is 7 Kelvin. So it's going to be equal to 0.383 kilograms per second divided by 259.18 minus 68.59 times CP, which is 1.005 kilojoules per kilogram Kelvin, times delta T, which is 7 Kelvin, and we get a mass flow rate of 0.0141 kilograms per second. Okay, so now we're finally ready to get the work put into our compressor. Okay, so now evaluating the work put into the compressor. So this is still A. We have W dot C is equal to M dot for R22, which we just found, H2 minus H1, which is 0.433 kilowatts. And remember, this is in. So another way you can denote in, I know that looks messy, that says in, is the negative sign. Okay, so B, we are looking for refrigeration capacity, so we need our Q dot in is going to be equal to M dot for refrigerant 22 times H1 minus H4 which will give us $2.69 kilowatts. And then we can do our conversion. So to get to tons, 2.69 kilowatts times 1 ton, and that's 211 kilojoules per minute times 60 seconds per minute. Or you can do the shortcut I did before. And that's going to give us 0.764 tons. All right, last part is the coefficient of performance. So beta is going to equal H1 minus H4, so the enthalpy change through the evaporator over the compressor. Okay, so just looking at this again. So Q in over WC. And this is going to give us 2.69 over 0.433, which is 6.21 for our coefficient of performance. All right, so with the last 15 minutes of class or so, let's go through and do a problem dealing with an ideal heat pump. Okay, so remember, a refrigerator is basically a reverse heat pump, is how that operates. So we're going to look at number 10.34 in your text. And it says, an ideal vapor compression heat pump cycle operating at steady state with refrigerant 134A as the working fluid. The heat pump provides heating at a rate of 15 kilowatts to maintain the interior of the building at 20 degrees Celsius. When the outside temperature is 5 degrees Celsius, sketch the TS diagram for the cycle and determine A, the temperatures at the principal states of the cycle, each in degrees Celsius, so the 4 principal states. And the states are given in addition to the pressure and their enthalpies to save time. The power input to the compressor in kilowatts, the coefficient of performance, and the coefficient of performance for Carnot heat pump cycle, so that beta max, okay? And so we're going to do that at the building interior and outside temperatures. So that 20 degrees and 5 degrees for the higher temperature and lower temperature reservoir. All right, so let's get to this. And so let's just jump right in at A. And let's figure out the temperatures at the principal states. And actually, while we do that, I'm going to go through and just take down the enthalpies and the entropies as well. Actually, I'm not even going to write down the enthalpies since they're in that table. So knowing that P1 is 2.4 bar, here X1 we find is going to be 1. If you look at your tables, you'll see that this is H sub V, this 244.09 kilojoules per kilogram, and that corresponds to a temperature of minus 5.37 degrees Celsius, and the corresponding entropy is 0.9222 kilojoules per kilogram Kelvin. So I'm just going to highlight our T1. All right, so let's keep going. I think this is 10.34. I don't even need this page. Yeah, 10.34. Okay, so next, let's do state 2. And so we're dealing with an ideal cycle. So we know that S1 is equal to S2. And so then we have to go to our tables and we interpolate, and knowing that P2 is 8 bar, we can find that H2 and we're given H2 is 268.97 kilojoules per kilogram. And we can go ahead and find that T2 is 35.72 degrees Celsius. So that's that one. So now for state 3, we know that P3 is 8 bar. Quality here is going to be 0 based on the info that they gave us. So we know H3 is 93.42 kilojoules per kilogram. That's given. So the corresponding temperature then under the vapor dome is 31.33 degrees Celsius. And the corresponding entropy is 0.3459 kilojoules per kilogram Kelvin. Okay, and then for state 4, we're dealing with a valve. H3 is equal to H4, and that's given. It's 93.42 kilojoules per kilogram. P4 is 2.4 bar. And so we can figure out that T4 is minus 5.37 degrees Celsius. All right, so now we have all our temperatures. So let's go back and look at our heat pump cycle. All right, so we're going through a compressor once again, and then into a condenser, then through a valve, and then through an evaporator. So it's very similar to our refrigeration cycle, except for the direction of Q in and Q out, if you are to take a look at that. So Q in, right? So here we're going to go, we're moving, we're doing the opposite as we were doing in the refrigeration cycle as far as the temperature reservoirs are concerned. Okay, so what we're going to do is, let's keep going, and we're going to find the power input to the compressor. Let's add it here. Okay, so the power input into the compressor is going to be, well, we need the mass flow, and so we know Q out. So let's use that. Q out is going to be m dot H2 minus H3. And so from there we can find that m dot is equal to Q out over H2 minus H3. And so this is going to give us a mass flow of 0.08545 kilograms per second. And then now our energy into the compressor, our power into the compressor is going to be m dot H2 minus H1. And because it asked in, we're just going to give the positive 2.126 kilowatts going in. All right, and so for part C, we're looking for the coefficient of performance. For a heat pump, it's gamma, and it's going to be Q dot out over WC. So it's going to be our 15 kilowatts divided by 2.126, which is going to give us 7.056. And then lastly, we're looking for our coefficient of performance if we had an ideal, if we had a Carnot cycle operating between, what was it, 20 degrees Celsius and 5 degrees Celsius. So it's going to be our gamma max. It's going to be equal to TH divided by TH minus TC, and we can use this temperature relation because we're looking for the gamma max for a Carnot cycle, and so if we convert it to absolutes, that would be 293 Kelvin divided by 293 minus 278. which is going to give us a coefficient of performance of 19.53. And then we can go ahead and we can make some comparisons. So yeah, it looks good. Our gamma is less than gamma max. If we look at what's going on for real with our cycle, here our TC for Carnot would be 5 degrees Celsius. So the evaporator temperature, so that's the outside. All right, so what is our lowest temperature that we're dealing with in our problem? Well, our lowest temperature is lower. We have minus 5.37 degrees Celsius. Okay, so we're lower, operating lower than this. And our TH, so the out for the Carnot cycle would be 20 degrees Celsius. Our TH is like 35. So we have a bigger span that we're operating over, and we're still not as efficient as a Carnot cycle, which would be reversible, and so that is a different ideal situation than the one we're dealing with here. So this is just ideal, but it's not a Carnot cycle. All right, well, that is all. And definitely post to the forum or email me if you have any questions. And you're almost there. You have one more prelim exam, homework 9, and then the final exam, and then donezo. All right, well, take care.